Let's start with a general problem statement in reinforcement learning. We've got environment, agent states of environment, agent's action, and the reward for a transition from one state S to another state S when with an asterisk by performing an action A. The agent interacts with the environment by discrete temporary steps. Every step T, an agent receives the current state as T and the reward RT. Obviously, there is no reward for a first step. Then agent chooses an action AT, which is subsequently sent to the environment. The environment transits to new state as T plus 1, and the agent receives the reward RT plus 1 in accordance with transition. Agent's goal is to learn pi policy that maximizes the expected cumulative reward. We are solving the problem of balancing pole on a card. Our goal is to prevent pole from falling, thereby obtaining the maximum reward by moving the card to the left or to the right. In this case, agent is a card. This diagram shows how it looks like for our task. The state of the environment based on 4 numbers, the position of card, card acceleration, angle of deviation of the pole from the normal, and the acceleration of the pole at its apex. Everything happens in the same way as in the general statement of reinforcement learning problem. The main idea of Q-learning is what if we had such an action value function Q with an asterisk, which for the state of environment S would say that reward R we would get by doing action A, then we could easily build a policy pi with an asterisk that maximizes our reward. However, we don't have access to such a function, but since neural networks are universal function approximators, we can easily build a neural network and train them to approximate function Q with an asterisk. Every Q function obeys Bellman equation. Such iterative algorithms converge to the optimal action value function as I tends to infinity. But in practice, this approach is very impractical because the action value function is evaluated separately for each sequence without any generalizations. This is why we will use a neural network to approximate Q with an asterisk. Let's represent our value function Q via a Q network with theta weights. Let's define our loss function as a mean square error. The first 2 terms are Q-learning targets, and the last term is predicted by Q network action value. By minimizing Li, we update the theta weights by training neural networks. In the beginning, our agent has no idea about the dynamics of the environment. Therefore, we must allow him to explore how he interacts with the environment. Gradually, he must increasingly use his experience along with research. We will choose an action corresponding to the maximum value of Q exploration with probability 1 minus epsilon, or with probability epsilon, a random action can be chosen to move to the left or to the right. This is called epsilon greedy policy. We'll also use experience replay buffer to train our DQN. It stores the transitions ST, AT, RT, ST plus 1 that the agent observes. allowing us to reuse this data later. By sampling it at random, the transitions that make up the buff are correlated. This has been shown to significantly stabilize and improve the DQN learning procedure. Let's look at what happens in the pseudocode. Firstly, we initialize our replay buffer D and initialize action value function Q with a random weights. Then, for episodes from 1 to M, repeat initializing environment state S1 and the time steps 1 to T. Repeat according to epsilon greedy policy, select action AT, which then executes action AT and get reward and the next state. Store the transition in reply buffer. Then for a mini batch of transition from buffer D, we are setting ground truth values YG according to the terminalist of state S T+1, and at the end we perform a gradient descent step to upgrade weights of our DQN. Here you can see the graphs of our model after 5,000 steps. We received the maximum reward and the loss fell down to 0. This is our model in the start of the training, and here it is when we end our learning process. Also, we've got a graph that shows actions that our network will perform depending on the angle and the acceleration of the cart. Blue movement is movement to the left, and the red is movement to the left. Thank you for your attention.
Thank you very much. Very interesting and good. I can see that you understand what is going on.